Thank you all for joining us for this fifth lecture of the Summer School on Dynamically Deformed Solids, sponsored by CREDDS. Today's presentation is going to be on strain rate dependence of plastic deformation in defect microstructures, presented by Amit Misra from the University of Michigan at Ann Arbor. Amit is the Edward DeMille Campbell Collegiate Professor and also the Department Head of Materials Science and Engineering at the University of Michigan at Ann Arbor. He received his PhD from that same University of Michigan in 1994 and then worked at Los Alamos for a number of years, where he eventually became a Los Alamos Lab Fellow, which is a major distinction because there are only a handful of those for the entire lab. His interests are in designing materials with enhanced functionality through understanding and control of interface and defect phenomena. So with that, Amit, I hand it over to you.
Thank you, Mike. I'm going to share the screen. It's a bit slow. Okay. Okay, so you see the screen?
Yep.
Okay, so let's get going. So thank you for the introduction. And just to remind where this lecture fits in the summer school, this lecture and the following two lectures will cover the dislocation level mechanisms of deformation in metallic materials. So you should see these three as a set or a module, and collectively they will be able to address dislocation level mechanisms. Today's lecture is more on the phenomenological aspects, which are the necessary place where you begin, but that's not sufficient. You have to learn about the atomistic and crystallographic aspects that will be covered in the next two lectures that will then set the stage for the subsequent presentations in the summer school. Will be more on the shock deformation, the experimental diagnostics, and the failure mechanisms. So the outline is a very brief introduction about the microstructures and why it is important to appreciate the microstructure before we can understand the deformation mechanisms. Then the lecture has two parts. The first part will be on thermally activated deformation mechanisms, concepts such as strain rate sensitivity and barriers to dislocation glide, activation volume, and Haasen plot analysis. And then we'll look at defect microstructures and deformed materials, initially at low strain rate and then at high strain rate, and be able to compare and contrast these. And finally, we'll refer to some homework problems about how to apply this to the various multi-phase materials that are being studied in CREDDS. We'll also be throwing in some surprise quizzes just for the fun. So the lecture is not a research seminar, so this is more a textbook level, and there will be concepts described through schematics, equations, and graphs. The slides are also the lecture notes, so put in sentences where it makes sense that you can refer back to later, along with the following two lectures. The prerequisite is a basic course on mechanical behavior of metallic materials, where at least there is an introduction to plastic deformation of metals and dislocation theory. So we will not be describing what is a dislocation and so on. So that is the prerequisite coming into this lecture. Some of these textbooks that I've used are very basic textbooks that are used in senior level courses or introductory graduate level courses in dislocation theory and mechanical behavior, and some more advanced level book chapters. So let's start with the idea of microstructures, and I just have two slides as introduction. In CREDDS, we are studying multi-phase metallic microstructures, and these are processed using advanced techniques such as additive manufacturing, physical vapor deposition, severe plastic deformation, and starting with cubic metals like, say, copper and iron or copper and moly. The way the material is processed create very complex microstructural morphologies that are hierarchical in nature, can have different shapes, and different length scales. Some very simple cases like a multi-layer structure can be described with a simple length scale, which is the composition modulation wavelength, or a bicontinuous intertwined structure, or a hierarchical structure like the one shown here, where there are two microstructures embedded one in each other, two kinds of morphologies and two kinds of length scale. One which looks like a vertical stripe pattern, and then these islands of one phase that have ordered arrangement of solute clusters of fine precipitates. So these kinds of microstructures are common in these advanced manufacturing techniques if you have multi-phase materials. The question is, what are the strain rate dependent deformation mechanisms in these microstructures? That's the research topic for CREDDS. But before we get into the research, it is important to review, especially for the students in the CREDDS, the textbook level information about what is known about thermally activated deformation mechanisms. An example of the microstructure that is shown here schematically is here. This is an ordinary copper and moly mixture. So copper is face-centered cubic, moly is body-centered cubic. If you do co-vapor deposition, which means you mix copper and moly from the vapor phase and grow a thin film at an elevated temperature, due to self-organization during growth, the microstructure that evolves is hierarchical in nature. It has two kinds of microstructures that simultaneously form. One is the matrix that is shown here. The scale of composition modulation is about 75 nanometer. You see these stripes of brighter phase, which is moly here, and darker phase that is copper. And then these islands of copper that inside have these stringers of very fine precipitates of moly. And the moly precipitates are two kinds. The very small ones are FCC, which is not the equilibrium structure of moly. And the larger ones, about 20 nanometer or larger, are body-centered cubic moly. So it's a complete complicated structure with many phases, many morphologies, many length scales. And so that's the ultimate goal of trying to understand the strain rate dependent behavior of these kinds of complex structures. But before we can do that, it is helpful to refresh the textbook level knowledge about what is known about strain rate dependent and temperature dependent deformation mechanisms of just plain ordinary FCC metals and BCC metals. So first I will start by showing what are the different strain rates. Most of you already know this, but generally the very low strain rates from say -8 to -5 per second would be characteristic of creep test. From about -5 to approximately 10 to the -1, or maybe going up to 1 or so, would be the quasi-static kinds of strain rates. And then the dynamic region starts when the strain rates become positive. For small positive, those kinds of tests are standard dynamic tension compression tests. And then the high-speed testing using impact bars, or going to even higher strain rates in the shock regime, greater than 10 to the 4. So that's the whole strain rate regime that material can be subjected to. So what would be the property of, say, ordinary copper? So this is, again, taken from a textbook. It shows the tensile strength of polycrystalline copper as a function of strain rate and temperature. The strength values are plotted in units of PSI, pounds per square inch. So this is 30 KSI, 30,000 pounds per square inch. To convert to MPa, which is the more common unit, you multiply by approximately 6.9. So this is 207 MPa is the tensile strength of copper at room temperature at a strain rate of 10 to the -5. If you increase the strain rate to say 10 to the +2, so this is 7 orders of magnitude increase in strain rate, the tensile strength increases to say 276 MPa. So there is an increase with strain rate, and if you increase the temperature, you see the strength will drop. So with increasing temperature, the material becomes softer. But the strain rate dependence is maintained, qualitatively at least, that the strength will still increase with increasing strain rate, which shows that the material strength is dependent on strain rate and temperature. This plot only goes up to strain rate of 100. So what happens if you go higher? So a couple of examples shown in this slide. So this one is the yield strength of copper, which is 99.99%. It was pre-strained to a value of about 0.15 strain at room temperature, and then reload it at different strain rates. And here we see the strength values as a function of strain rate. And you can see a strain rate dependence, and then a sharp increase in the strain rate dependence when the strain rate exceeds approximately 10 to the plus 4. So you can see that at higher strain rates, new mechanisms come in that will lead to even stronger dependence. Similar behavior in a BCC base. This is a low carbon steel. You can see they have shown different regions where you have strain rate dependence and temperature dependence. And above a certain strain rate, you see a sharp increase. And generally, with the lower the temperature, the stronger is the strain rate dependence. So we can summarize these by saying that in general, the flow strength of metallic materials is described by constitutive equations that link the flow stress with the strain rate, and temperature. So whenever the strength of a metal or metallic alloy is mentioned, it is dependent on these three parameters. So we have to know at what strain level, at what strain rate, and at what temperature. Plastic deformation is irreversible and path dependent. And the increase of yield stress with strain rate is more pronounced at lower temperatures and higher strain rates. We would now go into the second part, where we start looking into defining these parameters, such as strain rate sensitivity. So what is strain rate sensitivity? A general relationship between flow stress and strain rate at a constant strain and constant temperature is sigma to constant c epsilon dot to the power m, where m is defined as the strain rate sensitivity. This is measured in a mechanical test, which can be a compression test, a tension test, or even a nano indentation test, by doing what is called a strain rate jump test. Stress versus strain at a certain value of strain, at a strain rate of say epsilon dot 1, you have a certain value of flow stress, sigma 1. If we were to abruptly change the strain rate, like shown here, it is increased to a value epsilon dot 2, the flow stress increases to value sigma 2. And if you can measure that at a constant value of strain, then you can use this equation to calculate the strain rate sensitivity. It tells you how sensitive or how strongly dependent the flow stress is on the strain rate. Now, typically for bulk metallic materials, that value of m is very small. It is much less than 0.1. In fact, even much lower than that. For pure FCC metals, it can be as low as 0.001 or 0.005 or so. But it increases at elevated temperature. It also increases at higher strain rates. And to get a sense of the strain rate and what it can do, even though it's a sort of a side topic, I will remind of this phenomena of superplasticity. And noting that an extreme value of m would be 1, which is like a Newtonian viscous solid, where you can easily deform it or pull it in tension. In some materials at high homologous temperatures, greater than typically 0.5 melting point, very fine-grained metallic materials that have high values of m that have known to produce superplastic behavior, which is characterized by large tensile elongation, often greater than 1,000%, without the formation of a neck. So there are advantages of having a very high strain rate sensitivity. This is an example from titanium alloys and zirconium alloys, where you see the elongation and tension greater than 1,000% for very high strain rate sensitivities. This is an example from tin bismuth eutectic that was strained to 1950%. So getting back now to the thermally activated deformation mechanisms, I showed data for strain rate dependence. This plot shows data for strength of ordinary metallic materials as a function of temperature. So you'll see two kinds of behavior. One, FCC metal, nickel. Earlier I showed copper. And you'll see that the strength values are low and the dependence on temperature is also very low. Whereas for body-centered cubic metals, that dependence is very strong. And some of that, I believe, will be covered in the lecture next week. That has to do with the crystal structure and the dislocation core structure in body-centered cubic metals. It also affects the ductility, and some of these materials like body center cubic metals lose their ductility, and the temperature is reduced, and they go through this ductile to brittle transition temperature, and so they are not suitable for cryogenic applications. Tantalum seems to be a bit of an anomaly where maybe more work is needed. But you can see FCC metals generally do not lose their ductility going to lower temperatures. So there is an impact also on ductility. The activation energy for plastic flow, temperature dependence, can be given by this equation. So sigma is equal to epsilon to Q over RT, where Q is the activation energy for plastic flow, and it can be measured by a temperature change test, very similar to the strain rate jump test. But in this case, the temperature is changed, and the corresponding change in flow stress is measured at a constant strain. And we can then use the equation to calculate the activation energy for plastic flow. Now, both of these, there is a strain rate dependence and there is a temperature dependence. They can be combined into a single expression that was originally proposed by Zener and Holloman. So it is a Zener-Holloman parameter, where the flow stress as a function of the Zener-Holloman parameter, strain rate, epsilon to the delta H over RT, where delta H is the activation energy for plastic flow divided by the strain rate sensitivity. Plastic flow, therefore, is a thermally activated process, even if we are deforming the material at room temperature or even at temperatures below room temperature. It's always a thermally activated process. And the experimental study of the activation energy for plastic deformation and how that activation energy depends on the stress, the temperature, the deformation, the strain rate, and so on is one of the ways to validate the theoretical models for dislocation processes. So whatever is happening inside the solid at a dislocation level and how it interacts with the crystal structure, the microstructure, determines the macroscopic behavior that's measured. In fact, some of that shows up in an ordinary tension test or compression test, how the temperature change effects on flow strength and the strain rate change effect on flow strength can be directly related to the dislocation mechanisms through the treatment that will be described in this lecture. So let's now discuss a little more about the thermally activated deformation. So say there is applied shear stress tau that is moving a dislocation forward in the glide plane. That dislocation motion is opposed by a variety of internal stresses that arise from the crystal structure and the microstructure and the defects in the material. And say the sum of all those is given by tau sub I. Now, this internal stress, tau sub I, can be divided into two categories, or it originates from two kinds of obstacles. One is the long-range obstacles to plastic deformation. And since these are long-range over larger length scales and high enough barriers, they cannot be overcome by thermal fluctuation. So these kinds of obstacles are referred to as athermal obstacles or athermal barriers. And let's designate that as tau sub mu, and realize that this contribution to the flow stress is temperature and strain rate independent. Some of the examples will be dislocation arrays and pileups and alignment into sub-boundaries and etc. that form, or dispersoids or non-coherent particles. These have high enough barriers over a longer length scales that cannot be overcome by thermal fluctuation. The second kind of barriers that are more common are the short-range obstacles that could be even the lattice barrier from the crystal structure, from few atomic dimensions to hundreds of atomic diameters. Now, this is a case where thermal fluctuation can assist the dislocation to overcome these kind of barriers because they are more local and they are small scale, provided the thermal energy is high enough and there's enough time to overcome those barriers. So let's say the contribution from that is tau sub th star, and this is dependent on temperature and strain rate. Some of the examples of thermal barriers include Piles-Nabarro lattice resistance, strain field around solute atoms, very fine scale coherent precipitates, and dislocation unit mechanisms such as cross slip, climb, and dislocation interactions. All of these are examples of local and short range barriers. So the total is these two parts, and this is an important message to have, that we are overcoming two kinds of barriers, one that can be overcome by thermal fluctuations alone, and the other that cannot be, and that require mechanical work to be done by applied stress. We can plot it schematically as shown here. And so this is, we have the short range stress fields that are superimposed on a fluctuating long range stress field of some wavelength lambda. And this is the total internal stress, the opposing dislocation motion in this direction, which is some crystallographic direction on the glide plane. And the total is the contribution, which is athermal from the long range stress field, and the thermal contribution that's superimposed on top of it from the short range barriers. Now, clearly at 0 Kelvin, when there is no thermal assistance, then the applied stress for glide will be tau naught, which is shown here at the top. So all of this barrier has to be overcome by the mechanical work done by the applied stress. There is no assistance from thermal fluctuations. The rate controlling process, the part that's dependent on the rate, the temperature, is overcoming the strongest short range obstacles that is situated near the top of the opposing long range stress field. So that thing here, the tau star TH, that is shown in the schematic. So at finite temperatures, what happens is that thermal fluctuations can assist in overcoming the short range obstacles, and therefore the applied stress will decrease. And the limit when all of this contribution that's shown here, tau star TH, can be overcome by thermal fluctuation, the applied stress needed for glide will just be tau sub mu, because this is the part that cannot be overcome by thermal fluctuation and has to be overcome by mechanical stress. So we can now look at this barrier in more detail and say, what is the thermal activation barrier? You can think of it in terms of this force versus distance curve. And say you have a glide dislocation that is moving under applied stress tau star. The Burgers vector is B, so it has a force tau star B. And if it encounters obstacles with spacing L star, then the net force that's moving the dislocation forward in this direction X is tau star B L star, and that brings it up to this level on this barrier, up to the level F that is shown here. And then a dislocation comes and stops at this point X naught. In order for it to overcome this energy barrier, it has to move from the position X naught to X naught star. So it has to move this distance D star that is shown here, the distance that atoms will move to overcome that energy barrier. And that barrier is shown here shaded as delta H. So this is the energy that's needed to be overcome, and that can be overcome by, this represents the barrier from the short range obstacles that in principle can be overcome by thermal fluctuation. So we can say that delta H is the area under this force distance curve from X naught to X naught star, that minus the mechanical work done by applied stress during thermal activated flow. So that delta H is equal to delta H star, where delta H star is the activation energy for 0 applied stress minus this term that represents the mechanical work done, the contribution from the mechanical work. There is the thermal part is equal to the total minus the mechanical part. And the mechanical part is written as the applied stress times this volume. So this tau star B L star times D star, so B L star D star, so that becomes the volume. And so this volume is called the activation volume. So it represents the average volume that dislocation structure is involved in the deformation process to overcome this local barrier, the plastic deformation energy barrier. Now in this, we are using a delta H. A lot of the older textbooks use delta H, which is the enthalpy. You will also see delta G being used, and in other slides I will be using delta G, which is the Gibbs free energy for thermally activated glide. And it turns out some people had done analysis and there's not much of a difference in most cases which one is used. So just to reiterate that activation volume, which is a very important indicator of what is the kind of barrier that a dislocation is overcoming. If you could somehow measure the activation volume, you'll get a sense of the dislocation of Burgers vector B, what distance it has to travel to overcome that energy barrier that is associated with plastic deformation, which involves obstacle spacing and involves the distance the atoms have to move to overcome the barrier. So knowing a sense of that magnitude will allow us to interpret that in terms of what are the local barriers. If it is atomic dimensions, then it must be crystal structure, like the Piles-Nabarro lattice friction stress. If it's a few atomic dimensions, it probably is solute atoms. If it's hundreds of solute atoms in a cluster and so on. So that gives a sense of what is happening in a very phenomenological way. So this is therefore an important quantity which can give valuable information on the deformation mechanism, because it has a definite value and it has a stress dependence for each atomistic process. So this is where we would start. It does not give the complete picture. So you still have to do the atomistic level studies, and those will be discussed in the subsequent lecture. But this is a place you would start. Now, typically, this activation volume is expressed as an integer multiple of B cube. Where B is the Burgers vectors. Intuitively, it's easier to think of it in terms of how many multiples of, if you can say one unit volume is one Burgers vector cube, then how many Burgers vector cubes are involved, and that gives you a sense of the dimension around the dislocation that represents the barrier. Now, generally for bulk FCC metals that are large grain single crystals or large grain polycrystals, that activation volume is very large. It's about 1,000 B cube, which it is showing that the kinds of barriers that are being built are not the lattice resistance barriers. It is the barriers that come from creating dislocation cell structures, the dislocation forest and the more long range type barriers. And whereas this for BCC metals, generally it is a very small activation volume, which means that the critical barrier here is the lattice friction stress. It's an indirect measure, but it's very helpful to have this sense of measure. So now we just talked about the activation barrier. We'll talk a little bit about the kinetics, that thermal fluctuation, thermal at a given temperature, the thermal assistance that's available is KT, the Boltzmann constant times temperature. And if that energy is at room temperature, KT is 0.025 electron volts. At a higher temperature, it might be slightly higher. So if that is enough to overcome the energy associated with the short range obstacle, then in principle, thermal fluctuation can overcome it. The question is, will it happen in the time scale of the deformation process? So this is where it becomes rate dependent. So just because there is enough energy does not mean there is enough time. So for that, we have to think about it as the probability of that energy delta G occurring by thermal fluctuation at temperature T is given by the Boltzmann factor, exponential minus delta G over KT. And if the dislocation is vibrating by thermal fluctuation at some frequency nu, then it can overcome nu times that exponential term barriers per second. And if it moves a distance d star, then you can write an expression for dislocation velocity. It is the distance moved times the barriers overcome per second. So this becomes length per unit time. So this becomes dislocation velocity. Now there is a well-known equation, Orovon equation, which I will not derive, but I will introduce. This comes from basic dislocation theory, that for an imposed strain rate epsilon dot, it must equal the mobile dislocation density times the Burgers vector times the dislocation velocity. And so now that we have an expression for dislocation velocity, we can put that in this expression, which will give us an expression for the strain rate times this prefactor times the exponential of delta G over KT. So this expression shows you the interrelationships between the free energy of plastic deformation and the rate of plastic deformation. The temperature is in there. Delta G of course, will determine the flow stress. So there is a relationship between delta G and flow stress, and therefore there's a relationship between the flow stress and the strain rate. And so they're all kind of interconnected through these kinds of expressions. It's important to realize that's also intuitive from the Orovon equation that as the strain rate increases, to meet that strain rate, either the mobile dislocation density has to increase, or the dislocation velocity has to increase, or both, some combination of both, which means that either you are generating more dislocation sources or just making them run faster. And so that gets into what kinds of barriers are there, and will those barriers be overcome in the short time scale as the strain rate is increased. And so at a given temperature, if there is enough thermal energy to overcome the barrier at long enough time, does not mean that the same thing will happen at a shorter time scale. So if we increase the strain rate, the kinetics will come into play, and even if the temperature has enough energy, the short range barrier may still not be overcome just because there is not enough time. So that sort of is the physics behind these kinds of relationships. So just to recap this part of the presentation, the concepts is the energy which has to be provided for dislocations to overcome the barriers they encounter during slip determines the dependence of flow stress on temperature and applied strain rate. If the energy barriers are sufficiently small for thermal energy, which is kT, to be significant, thermal vibrations of crystal atoms may be able to assist the dislocation to overcome the obstacles at lower values of applied stress than at 0 Kelvin. And these conditions, you'll see a strain rate and temperature dependence. So a decrease in temperature or an increase in strain rate will increase the flow stress. So this is describing the theory. And now we can begin to apply and say, okay, how are we going to measure activation volume, and how do we make sense of what we measure? So at this stage, we will take a quick pause. And I have thrown in some of these trivia quizzes. The hope is to continue to have fun and make sure everybody is awake. So the way it will be played is I will put up the question, and you can write your answer in the chat box. I cannot see the chat box, but I will have Michael announce the winner. So the fastest finger who writes the first correct answer. So here's the question. Which is the only university in the nation located on its own island? I'll wait 10 seconds. Get a drink of water. So I cannot see the chat page. Hopefully some of you attempted. I did a search. Somebody wrote University of Hawaii. Cornell, Iceland. I'm happy to see that students are attempting. You don't lose any points by trying. So yeah, this is meant for fun.
Can I try?
Yeah, you have to write in the, okay, somebody wrote the correct answer. So this is whoever is the first person to write. This is Texas A&M, not College Station, sorry. This is Corpus Christi, beautiful looking campus. If you have not had a chance, you could go visit. Okay, so hope you enjoyed that. There will be a few more of these coming along, so stay tuned. So we will now talk about how activation volumes are measured and how those are interpreted in terms of what is known as Haasen plot that comes from Pete Haasen's work. This is the original reference, 1958. We talked about plastic deformation of nickel single crystals at low temperatures. Now in these plots, what is done is the inverse of activation volume is plotted as a function of flow stress minus the initial yield strength, sigma minus sigma y. So this, starting with that expression that I introduced before, strain rate, some pre-factor here, and then delta G, which is a function of the stress times kT. You can write, we won't go into the derivation, but essentially activation volume can be written as M times kT, and the differential of natural log of strain rate with the flow stress at a constant temperature, where m is the Taylor factor. So you see two kinds of stresses used here. One is tau, which is the shear stress. All the equations that deal with the shear dislocation motion start with the shear stress, because dislocation responds to shear stress in the glide plane. So they're always written, but experimentally what is measured typically is the uniaxial stress by doing a tension test, or even if you do a hardness test, you never typically don't directly measure the shear stress. So we have to convert it. And that is done by multiplying with this Taylor factor, which is approximately 3 for FCC metals, also for about the same for about BCC metals. So activation volume is mkt, del of a log of strain rate over the stress. So if you could measure that quantity that's shown in the red box here, if you can measure that change in flow stress as a function of change in strain rate through different kinds of tests, like a load relaxation test, stress relaxation test, strain rate jump test, if that can be measured, then you have that quantity, and then you can calculate the value of V. And previously, I realized I use V star, and so here I'm using V. Just to be clear, it's the same thing. It is activation volume. So with that, why do you plot it as a function of sigma minus sigma y? That will become clear. I will show you an actual data. Very busy plot. I will walk you through it. It is from high entropy alloys, which are studied a lot these days. And the original references are here. So this is not from textbook. So this is Isa George and others. They have worked on this, especially this paper by LaPlanche. This is Actamet. Sigma or del log of strain rate. And it has units because of the sigma in the numerator, units of MPa, and which is equal to mkt divided by these kinds of calculations. Just try it out to see that the units will match, that this will be units of MPa, because you see Boltzmann constant temperature divided by volume will give you units of MPa. You can do a calculation where you say mkt over V equals 2 and calculate what the value of V is. On the x-axis is sigma minus sigma y. So value of 0 on x-axis means sigma equals sigma y. So that is the yield stress. So the value of the activation volume, or the inverse of it that's plotted here, is the initial yield stress that in this case comes from solid solution. So we don't have a single element FCC. It is a solid solution. In this case, it is iron, nickel, chromium, cobalt, manganese, equiatomic percent. And so that is the activation volume that is being measured for that solid solution. As you continue to strain it at a constant temperature, so this is room temperature, as you continue to strain it, the material will strain harden. So as the strain hardens, you can then plot the increase in flow stress, which is flow stress at any given strain minus the initial yield stress, and you'll see that that increment is plotted here. And that is the strain hardening, or what is called the forest hardening. It has a linear relation, which is called the Cottrell-Stokes law. And so this is, from this plot, you can actually, and this is a fairly simple measurement that's become a routine. I will show you an example with the nano indentation. So you can do these calculations on your own. If I try to do that calculation, I find that it gives me an activation volume from this of about 6 nanometer cube. 6 nanometer cube as such doesn't mean much, but if you were to write it as in terms of multiples of Burgers vector cube, you'll see it's about a few hundred, say about 300 to 400 Burgers vector cube. And so from this, the authors were able to argue that the high entropy alloys do not show any different kinds of mechanisms. So you would get a similar kind of number if you had a solid solution FCC alloys. So which means fundamentally that doesn't change into a different kind of order of magnitude. It is the same type of mechanisms, it's just the magnitudes might be a little different. If you do the same for BCC metals, so you see here, this is the inverse of activation volume. So if you're moving up, the volume will get smaller. So for BCC high entropy alloys, so this is titanium, zirconium, hafnium, niobium, tantalum, you're getting a value of 1.5 nanometer cube. Or for that Burgers vector, about 70 times MB cube. So this is also showing that you still have that lattice resistance that is, it's more local than what you have. So here is more solute clusters, but here the activation volume is even smaller. So it is coming from more local piles and borrow type of barriers that are still active. So there is, of course, on top of that is solute atoms. It is, if there are multiple mechanisms, then it becomes difficult to deconvolute. And in this lecture, I'm not going into the detail, but if you are interested, I could give you references where those have been tried in a phenomenological way. The math becomes really messy because you have to make a lot of assumptions. And it also shows that you need other kinds of ways to probe the atomistic level mechanisms if multiple mechanisms are involved. The lattice friction stress plus the solute atoms, and how do you deconvolute? This is showing you the complete case here. As I mentioned before, the linear part here, the forest hardening that is shown here is basically the Cottrell-Stokes law. This is the dislocation strain hardening from the dislocation forest, where the forest activation area scales at 1 over square root of the dislocation density, essentially the mean spacing between dislocations. So 1 over square root of rho is equal to the mean spacing between dislocations that are being statistically stored inside the crystal as it is deforming. And the flow stress, which is the Taylor hardening, scales with the square root of the dislocation density. So how are some of these measured? A lot of people in CREDDS do experiments with nano indentation. So this is a reference. There are many other recent references where there are protocols that have been developed with standard nano indentation platform where you can do these strain rate jump tests. So here's an example. This is a coarse grain steel and a nanocrystalline steel, and this is the indentation load and unload indentation depth curve. And at fixed indentation depths, they change the strain rate. So from 0.05 to 0.005. So they programmed it so that it will load up to a certain strain rate to a certain depth, and then abruptly the strain rate will change. It can get lower or increase, lower, increase. And like that, when you were to interpret the hardness as a function of indentation depth, which is hardness here shown as indentation depth, you will see little blips. So the hardness will change at the point where strain rate was changed. I apologize, it's difficult to read, but you will have the notes. If you take this red box here and blow it up, you could see the hardness drop as the strain rate was lowered from about 6.9 GPa at strain rate of 0.05 to about 6.6 at strain rate of 0.001. So it's possible to measure these parameters, and you can see in these studies they have calculated activation volumes for different kinds of materials. I'll show a couple of examples for material systems that are of interest to people in CREDDS. This is a copper niobium composite. This is made by high pressure torsion. So it is severe plastic deformation, different from ECAP, but it's going to produce microstructures that have fine, not nanocrystalline, but at least ultra fine grain. And it makes the material very strong. So hardness is about 5.3 GPa. For copper and niobium, it's very strong material at room temperature, and they measured the hardness would drop with increasing temperature. They were able to measure the strain rate sensitivity by using nano indentation, and they were getting values of about 0.025 at ambient temperatures that would increase with increasing temperature to about 0.1. They are getting measures of activation volume. So this is the expression I showed before. We had written it as inverse, and I had capital M for Taylor factor. Here they have used square root of 3. They are getting data from indentation. But essentially, you are able to measure activation volume as a function of temperature. So they were able to do indentation also as a function of temperature at different strain rates. A lot of these are still quasi-static, but you are able to measure strain rates and see that you are having activation volumes that are a lot smaller than what you have in bulk copper. So there is an effect that's coming from the finer sizes, dislocation density increase, and possibly also having a body-centered cubic phase. It's difficult to deconvolute, but it's a place where you would start to see how things have changed. Another example, so this is from indentation tests where you're measuring hardness. You can also do compression test, which has become very common nowadays in nano indentation. Micropillar compression test, sorry, let's go back. This is work from John Carpenter, who is now at Los Alamos. This was his PhD thesis at Ohio State. And these are materials, copper, nickel, that were made at Los Alamos. They are epitaxial. So in this case, you have FCC coherent or semi-coherent systems. And he was able to do these micropillar compression tests. All of these are low strain rates, so from -3 to -5, and measure the strain rate sensitivity and activation volumes and compare it to the coarse grain nickel and copper. So you see for coarse grain FCC metals, the value of M is very small as 0.001. Activation volumes, as I showed before, is about 1,000 B cube. For these multi-layers, these are much smaller. So you're seeing an effect of the fact that you have introduced additional barriers, interfaces that contain dislocation in those interfaces, how things might evolve with those kinds of microstructures. Nanocrystalline metals, FCC metals, when they are nanocrystalline, also show a difference in activation volume. So the activation volume is much smaller. It actually is comparable to what you would see in BCC metal, but for a different reason. In this case, you have introduced grain boundaries at finer scale. So there is an effect of microstructure change that can affect this. Okay, so at this point, we'll do the second trivia quiz. So you know the drill. I'll put up the question and the fastest finger first. So let's see, now you know what to expect in the surprise quiz. Which campus is located on more than 1,000 acres of ocean coastline? And according to some, it looks more like a vacation resort than a college. A lot of people got it. That's the correct answer. This is what Newsweek said about, if there is a more beautiful campus than this one at the edge of the Pacific, we haven't seen it. There probably are some people from UCSB on this call. If they are not, then you know where they are. They are probably on the beach. Okay, so let's continue on to the second part. So we introduced these concepts of thermally activated deformation mechanisms, thermal barriers, athermal barriers, activation barrier, activation volume, the measurement through Haasen plot. Let's now begin to look at dislocation substructure, which is the second part and the final part of this lecture. So I'll first show the defect microstructure evolution at low strain rates and then at high strain rates. So at low strain rates, this is a very classic textbook image that you will see. And you see here the shear stress and shear strain for a single crystal that has been oriented for single slip. So it shows all the different stages, starting with elastic region, and then goes into plastic with a very low slope. This is the shear stress. It's a very low slope. So theta 1 is the strain hardening rate. And then you see the strain hardening rate increases rapidly in this stage 2 strain hardening. And then it starts to flatten out, so to speak, flattening the curve in a different context. You can now lower the strain hardening rate. So this is the stage 3 strain hardening. So you start to get multiple slip systems. You go from single slip to multiple slip with a high rate and multiple slip with dynamic recovery. What happens to the dislocation structures in each of these stages? Single slip, it's very easy to understand that you only have a single slip system active. Dislocations are gliding as planar arrays. There is very limited interaction except for these dipoles that might be coming close enough, and there might be some attraction repulsion that may be setting up. But otherwise, in general, there's not much interaction between these parallel dislocation arrays. So you don't get much strain hardening if you have single slip on parallel planes. But once you get to multiple slip systems and dislocations start interacting, then you start to build a tangled structure that's often referred to as a forest. And you get into a forest hardening that any new dislocation has to be gliding across this tangled mess of dislocation that are formed, that have locked into each other by various kinds of dislocation mechanisms. Some of it may be described in the lecture weeks, but I won't go into much detail at this point. Maybe just give you one example of a common, like how do two dislocations that are gliding lock into each other. So for FCC metals, you have Burgers vector A over 2, 1, 1, 0 on a 1, 1, 1 plane. And if, say, a dislocation with this Burgers vector, the way it is written here, A over 2 minus 1, 1, 0, were to intersect with a dislocation with Burgers vector A over 2, 1, 0, 1, they will react, and energetically it's favorable by Frank's rule to form a product dislocation. This will have lower energy overall. So this product dislocation forms, except that it gets stuck on a plane which is not a glide plane. So this dislocation with Burgers vector 0, 1, 1 does not lie on either of these glide planes. And you can do that, the dot product, and see. Now, because it is not contained in any of these glide planes, it is a sessile dislocation. So that's how you create a lock, where dislocations combine with each other to produce a product dislocation that is sessile, because it is sitting, the Burgers vector does not lie on a glide plane. Now, if you were to do the same thing with partial dislocations, you'll create a Lomer-Cottrell lock. That's a little more involved, and maybe some of that will be covered in the next lecture next week. But it's trying to show you how dislocations can create these locks that are difficult to break, and that leads to high strain hardening rate. Eventually, what happens is thermally activated mechanisms such as cross-slip become active. Dislocations can overcome these local barriers, and that leads to a self-organization of dislocations into these cell walls, where you have relatively dislocation-free structure. You look very clean grain and high dislocation content along these walls that eventually become low-angle grain boundaries or sub-boundaries. So this gives rise to a lower strain hardening rate. Now, of course, this is dependent on the ability of dislocation structures to be able to cross-slip from one plane to the other, and therefore dependent on the material properties. And you see a very different behavior depending on the ability of a material dislocations to undergo cross-slip, which is related to its stacking fault energy. So generally, the most well-defined cell structures form in metals that have a high stacking fault energy, because dislocations can easily cross-slip. The partial separation is very small, and so dislocations essentially move like a full Burgers vector. They can easily cross-slip from one plane to another. Aluminum is the best example of a high stacking fault energy material that will easily go into the stage 3 and show a lower strain hardening. Copper and nickel are intermediate. You'll see, in this case, you see a cell wall structure forming, but hasn't formed a clean subgrain structure like in aluminum. On the other hand, the least well-defined cell structures form in low stacking fault energy metals, such as copper, aluminum, even brass, copper, zinc, FCC copper, zinc alloys, austenitic stainless steels. A lot of the FCC high entropy alloys are in this area, where you get the cross-slip is difficult because the stacking fault energy is very low, so the partial spacing is very large, and so a lot of the deformation is partial dislocation controlled. And where cell structure forms, the dislocation cell size shown here scales with increasing strain. So here the cell size can go from about a micron, which is like you see here for aluminum with the scale of a micron, to about 0.4 micron, like what you see here with increasing strain. So this is what would happen, the kind of deformation structure that would form with increasing strain at a low strain rate. So what would happen if we were to increase the strain rate? So generally what happens when you increase the strain rate, the common defects that form would be, of course, dislocations. You'll get a lot more of partial dislocation, especially in materials that have low stacking fault energy. You get the significant difference is there's a lot more deformation twinning. It's the number one change that you would see at higher strain rates. There's also point defects that form, vacancies and interstitials, and sometimes you can have martensitic phase transformations. That is not covered in this lecture. Now, in general, the defect microstructure that forms at high strain rates is comparable to what happens at low strain rates at cryogenic temperature. You get you can get twinning even at lower temperature. And why that happens, the concept behind that we'll describe in a subsequent slide. So before we show TEM images, there are a number of students who do not have background in transmission electron microscopy, maybe because they don't have material science background, or maybe they do theory or atomistic modeling. So simple questions are asked is, how do I know what is a stacking fault and what is a partial dislocation, what is a twin? If I look at a TEM image, how can I tell? So I'll have a couple of slides of like a tutorial of how can you tell or what things to look for. So this is an example of twins in copper. And here you see these planar defects in copper. This was actually in a physical vapor deposited film. So this is from growth, but it doesn't matter how it formed. These defects are twins. And the question would be, how do you know they are twins? So that it produces signature in electron diffraction. And you see here the corresponding electron diffraction pattern. And this is a 110 zone axis pattern. And you can see the spots here. The signature of a twin is what is called here the spot splitting. So instead of one spot for the 200 plane, you see two spots, spot splitting. And the spot splitting happens across the mirror plane, which is the twin plane. So if I were to extend that twin plane, you see the spot splitting across that mirror plane. The only spot that does not show the splitting is the twin plane itself. So in this case, it is a 1-1 bar 1 plane. So that is because for the matrix and the twin, it's the same plane. So that does not show. But for everything else, because the crystal inside the twin has a mirror symmetry, you will get a spot from the twin and you get a spot from the matrix, and they are related with this mirror symmetry. Notice that you have the diffraction pattern is simply the fast Fourier transform of a lattice image. So if you had a lattice image, so this is a high resolution image. This is another way to look at if you had a high resolution image. So this is matrix, twin, matrix. There's a twin boundary, there's a twin boundary. So you will notice two things here. These are the 1-1-1 planes. It's the other 1-1-1 plane. We are looking down the 1-1-0 axis in FCC. So you'll notice two things here. One is that there is a mirror symmetry across the twin plane. And this is how you can verify each atomic position, the column of atoms, you'll see a mirror image across, which is very classical zigzag pattern that is produced. So that's the signature of a twin boundary. And also, if you were to just do a fast Fourier transform, so that diffraction pattern was obtained by doing a fast Fourier transform. If you had an atomistic model image, you can do the same with atomistic model image, and you'll get a diffraction pattern like this, which is the reciprocal lattice. And you'll see that you have these diffraction spots. The ones that do not show splitting are the ones corresponding to the twin plane. So normal to that is here. So this is an example of twinning. It's become important nowadays. A lot of in situ testing is done in nano indentation. This is an example from a high entropy alloy that was tested in situ in a pico indenter in a TEM. And as the material was being tested, these features started appearing. These dark lines started appearing. And the question would be, what are these? Are these dislocations? Are these stacking faults? Are these twins? And they have shown here the time scale. This is 9 seconds, this is 41 seconds. So as they're pulling it, these little nano ligaments are forming these deformation twins, as it turned out. And the way they could tell is by doing a high resolution imaging of this defect. And they could see the twin structure here, the matrix and the twin, the mirror symmetry. This is a way you can tell what that defect is. Likewise, in a similar study, as they were doing a tensile straining at the tip of a crack, they were able to see these features form. So these are defects that look very planar, almost like a plane intersecting the surface of the foil. And these turned out to be stacking fault. So how do you know it's a stacking fault and not a twin? You see the diffraction pattern does not show the split spots. And when they do the high resolution imaging, as is shown here, they were able to see something form at this location where the lattice planes are perturbed. And when they were to blow it up and see, you don't see the mirror symmetry. You don't see the zigzag, but you see the A, B, C. The next plane, the stacking sequence is disrupted. This can also be simulated with atomistic modeling, and that can be superimposed. And that analysis will show you that there is a stacking fault here. A, B, C, and the A plane is missing. B, C, A, B, C, and again the A plane is missing. So there's a fault here and there's a fault here. So this is how you can tell in high resolution There is another way to tell stacking faults. Oftentimes in bright field imaging, what would happen is if there's a fault that's spanning the entire width of the TEM foil from the top to the bottom, what it is doing is that it's creating a disruption in the lattice planes that go across, and a shift by delta R, where delta R is the fault vector. For FCC, delta R is 1/3 111. And so this is going to produce a contrast because there will be interference from lattice planes above and below the fault that have undergone a shift by delta R, corresponding to the magnitude of the fault vector. And the contrast will depend on these parameter, the reflection vector, the diffraction vector that's used to image dot product with delta R. And if that product is 0, then you don't get any contrast. And if the product is not 0, then you'll see contrast like these fringes. And that is very typical of a stacking fault contrast. And in this case, this is the reference here. It's from the same paper from high entropy alloy. They have seen stacking faults on 3 sets of 111 planes, creating like a parallel pipette structure. It's not a single fault, it faults on 3 different 111 planes. Sometimes you can get faults on all 4 and create like a stacking fault tetrahedron. So these are ways to know, and now it's time for our third trivia quiz. So get ready, the question is coming up, and you can read yourself. Hands-on experiential learning. Somebody said Penn State. Justolipia, I don't know if I'm pronouncing it right. They set a record, 43,000 gallons of ice cream produced at the campus creamery in 2014. Wisconsin, keep going, keep guessing. Somebody likes Cornell. No. Keep guessing, I haven't seen the right answer. Michigan State. Michigan Tech. By the way, there are a lot of, these are all good guesses because all of these campuses, especially Penn State, have these kinds of dairy creamery. There are people on the call who should know this answer. And the answer is University of Connecticut. If you visit, you can see they were pioneers in Penn State and Wisconsin, Madison, and many others have these kinds of creameries. But this particular fact, this particular kind of cheese, and these statistics of how many gallons of ice cream that comes from the data on the website of University of Connecticut. So continuing on, now the last few minutes will be defect microstructure and high strain rate deformed. And some of the images that I will show come from shock loading, although it shouldn't matter in many cases with high strain rate, you will get similar kinds of microstructure. The message here is to show how you will start with the kinds of dislocation microstructure that I showed before for the low strain rate, and how they start to change with increasing strain rate or increasing shock pressure if you're doing a shock experiment. So this is a plot taken from the Myers textbook, and it's showing shock pressure as a function of the pulse duration. You can just take this for nickel. You can take a constant pulse duration, 2 microseconds, and just move up as a function of shock pressure. And you could see how the dislocation cell structure evolves from looking very similar to what it would be if this was just strained at low strain rate, dislocation cell structure beginning to form. And as you would increase the strain in a low strain rate, what would happen is you'll increase dislocation density, cell structure forms. Same type of thing is happening here with increasing shock pressure. But eventually what happens is you start to form twins at high enough shock pressure. And in some materials, it's easier to form twins than in others that we'll look at in more detail later. Generally, in medium to high stacking fault energy materials, you'll see dislocation cell structures, aluminum, nickel, copper. This is similar to the stage 3 strain hardening. And in high stacking fault energy, materials cross slip will favor the self-organization of dislocation. So you can get straight away into the stage 3 strain hardening. with increasing stress and increasing pulse duration. What happens with twinning is the twinning depends on the shock condition. So this is 15 gigapascals, 30 gigapascals. You can see the twin volume fraction increases and the twin spacing decreases. You can get fine scale twin structure formed by doing high strain rate deformation or shock deformation. But in the case of low stacking fault energy materials, the previous slides were for nickel or higher stacking fault energy material. This is for austenitic stainless steel. And this is an example. The lower one is iron with 15 chromium, 15 nickel. By the way, if you were to just add cobalt and manganese, then it becomes the high entropy alloy, the popular high entropy alloy. We'll see that for many cases, the high entropy alloy behaves very similar to austenitic stainless steel with low stacking fault energy. In this case, you're not seeing the cell structure form. So it is still showing the tangles. You see all these dislocation tangles. So this is showing something similar to the stage 2 strain hardening. You can see appreciate the difference between the dislocation structures that form at higher strain rates depending on what the material properties are. In BCC metals, so this is an example from BCC metals, here also you don't see the cell structure form. So a lot of the dislocations that are produced still look dominated by the long straight screw dislocations that you would see if you were to do a low strain rate deformation. So here also the high strain rate deformation, at least in this case, the shock pressure up to 7 GPa has not changed the dislocation structure that forms. There is also, the final thing I'll show is that you can produce point defects also. This is aluminum shock loaded to a pressure of 13 GPa at liquid nitrogen temperature. From the mechanism proposed is the non-conservative motion of jogs and dislocations that might produce point defects that can be measured. Vacancy concentrations have been measured by electrical resistivity. The samples were shocked at liquid nitrogen temperature, recovered and stored at liquid nitrogen temperature. And so those have been measured. Sometimes you'll see vacancy loops in TEM. So this is image taken from Meyer's book where they give courtesy to Rusty Gray at Los Alamos for this TEM image. So if the dislocation loops are large enough, you can see in TEM, but otherwise you have to use these kinds of measurements like electrical resistivity to measure point defect concentrations. Now, twinning, that is favored deformation mechanism under shock loading. It depends on a number, it depends on a number of material and shock wave parameters. Generally, higher stress favors twinning, and minimum stress at which twins are observed depends on crystal orientation. Higher pulse duration, which means the threshold time there is a threshold time for twin nucleation. Lower stacking fault energy clearly favors twin nucleation. Lower initial dislocation density favors twin nucleation, and larger grain size. A lot of these are empirical observations. Some of these can be explained, and some are just hypotheses. A very simple schematic that is used to explain the difference or the balance between when you get twinning versus slip is shown here. This is stress normalized with shear modulus as a function of temperature. And you see the temperature dependent flow stress that we talked about in this lecture at low strain rates. On the other hand, the critical stress for nucleating twinning that to a first order does not depend on the temperature. So you can draw it as, you can approximate it as a horizontal line. And the crossover determines the temperature below which the twinning stress is lower than the dislocation glide stress. So here, because of the thermal dependent flow stress, the temperature is low enough that thermal activation cannot overcome the short range barriers, so the stress has to be increased for dislocation glide, unless there is another mechanism that can get activated. So twinning can get favored in materials below a certain temperature. However, if we were to do a high strain rate or dislocations moving at high velocities, in that case, this curve gets shifted up. The twinning curve remains where it is because the twinning stress does not depend so much on strain rate to a first order. And so what would happen is the crossover point gets shifted to higher temperature. So normally materials that show deformation twinning at cryogenic temperatures, you can see deformation twinning at room temperature if you were to do high strain rate deformation. And that's because of this. You have shifted the balance where the twinning stress is lower than the dislocation glide stress at the temperature at which the test is done. And finally, I will show that you can map out the stacking fault energy versus the critical twinning pressure in shock. This also is taken from Meyer's book. And you have two regions where you have higher stacking fault energy and the low shock pressure. So that's where you get dislocation cell structure. When you have lower shock pressure and lower stacking fault energy, then you get stacking faults. And higher shock pressure and low stacking fault energy will give twins. And that continues on. If you want to get twinning in nickel, you'll have to go to higher twinning pressure than, say, in case of brass. This is a very simple way to map it out and see where you would expect deformation twinning as a function of the material property and as a function of the critical twinning pressure under shock deformation. So that concludes the PowerPoint presentation, and I will show the last trivia quiz. For those of you who are still, it's gone just a little over an hour, so those of you who are still on the call, here's the question. See if you can pronounce the name of that university. I think you got the right answer. This is University of Michigan. It was founded in Detroit. Ketol Epistemiad was found in Detroit in 1817 and moved to Ann Arbor in 1837. And if you have not had a chance, this is a treat. We may not be having football this season, but eventually when it gets back to, if you have never had a chance to watch a football game, this is the place to do it. The big house, a capacity of approximately 107,000 people. The last part in the lecture is application to the multi-phase metallic microstructure. And I'm going to do it with homework problems. So we have to have a reason for you to come back to the call on Thursday. So I'm going to now finish by introducing 4 homework problems. And homework problem number 3 will cater to that point. So first homework problem, this is for fun. What do you like the most about performing research remotely, which is working from home, so to speak? All of us have done it for more than 3 months at least, if not longer. And there is no single answer. I would like to see if there is a consensus towards a majority or a popular answer, but I don't think there is a single answer. So I expect the responses will vary, certainly on the humor scale. So think about it and be ready to type your answer in the chat box. In the Q&A session or the office hour or review session, whatever you want to call it on Thursday, that's question 1. Question number 2 is draw a schematic plot showing the dependence of flow stress of a metallic material on temperature and indicate how it will change with increasing strain rate. So without having to refer to the lecture notes based on what you learned from this lecture, you should be able to just draw it. I think that's the key message to take home. Without having to refer to any lecture notes, you should be able to draw it and understand why that is the case. Question number 3, so this is what I mentioned was the 4th bullet point in the outline, is in the case of these kinds of materials, I showed a couple of examples, but I did not describe in more detail because I wanted to save it for the Thursday session. And the question to think about it, is there a size effect? Generally, we talk about a size effect on yield strength. Is there a size effect on strain rate sensitivity and activation volume, and why? And especially if the size effect is coming from these interface boundaries. We often study these nanolaminates, FCC, BCC, like copper iron or copper niobium or copper tantalum as model systems, but a lot of these are also examples that you will see in like ferritic austenitic steels, the same kinds of interface boundaries. If you were to reduce it to very fine scale, would you see a change in Y in strain rate sensitivity and activation volume? The last thing I did not touch at all, but you can think about it, is can strain rate sensitivity be negative? We talked about low values, but can it be negative? which means increasing the strain rate makes the material softer. And if so, then propose a plausible deformation mechanism. So that's the end of my homework problems and presentations. So I'm going to stop here and hand it over to Mike to see if there is any question for now. If not, then we will do questions on Thursday.
Thank you, Amit. So the floor is open to questions. What I suggest is if you have a question, please type it into the chat box and I will read it out so that it gets recorded for everybody to hear. So any questions? Okay, we have a question here from Peng Zhang. The exponential term comes in the equation for plastic strain rate through the Boltzmann factor, which is used to represent the probability of a dislocation to be activated. Why is the Boltzmann factor used?
This is referring to statistics of dislocation overcoming the barrier. That there is a finite probability that is going to overcome. And so that's why you cannot assume that every dislocation will overcome every barrier. So in this phenomenological treatment, that's how they ended up doing it, to assume that there is a probability. In reality, if you could, then you would be able to, through simulations or experimental measurements, and they have, so there's a follow-up question I see that exponential form is what they normally have for activation barriers. Whenever you have an activation barrier, normally that's what they would use. I don't know whether it's the best way to do it, but that's the common place you start when you have an activation barrier.
I would suggest as another piece of input that this is really coming from transition state theory. That anytime you have a thermally activated process with an energy to activate the process, then transition state theory, at least in the solid state, will tell you that you're going to get this kind of Boltzmann factor, or to be more precise, an Arrhenius factor, right? Because we're talking about rates here.
That's right. Arrhenius is a good way to say it. Yep.
Okay, I'm going to take it to the next question. Activation volume often compares to Berger's vector. So do we also have activation volume for amorphous materials?
That's a good question. I think you have to think of it in a different way, that in terms of shear transformation zone volume. And those are, if you are interested, I can send you some references where those treatments have been. So these kinds of measurements have been done, but they think about it in terms of the size of the shear transformation zone in metallic glasses.
And if I may follow up again, that's actually one of the earliest forms of experimental evidence for the shear transformation zone theory, is that the activation volumes are approximately of the order of magnitude of a shear transformation zone. Okay, next question from Bruce Remington. Has anyone studied high entropy alloys at high pressures in excess of 100 GPa and high strain rates greater than 10 to the 6 per second?
Very good question. Not to my knowledge. I think there have been some rate dependent studies, but those are not at the rates you are talking about. And I think that may be an opportunity area for us, to study. There are different kinds of high entropy alloys, and some are single phase, and some are what they call compositionally complex alloys that may contain finer scale second phases. And it would be of interest to, yes, do those kinds of experiments that I don't think have been done.
So far, I've butted into every answer, so I'll just continue that tradition. There is, I guess, evidence that some high entropy alloys have rather unusual cryogenic mechanical behavior at cryogenic temperatures. Yep. Is that, Bruce, one of the reasons why you're asking?
Yeah, Bruce, you can unmute and
you can unmute yourself if you want.
No, I was asking in the context of thinking about doing this on a laser where you can take the pressures up to high values and the strain rates are necessarily high. And it just struck me as you were speaking about this, it just struck me that I had never thought of that before, and it might be a new territory to look into. We could certainly do the experiments. The question would come down to, are there ways to interpret it?
Yeah, this is also the kind of strain rate that you can explore with atomistic modeling, except they don't have good potentials for high entropy alloys.
It'd be brand new territory for potentials.
Yeah, it would be a whole new area of research there.
We need someone on the team who would be happy to work on, potentials to plow forward. It's worth pursuing. I sort of like the idea. I just hadn't thought of it before.
Yeah, it's a good idea. Yeah, I think Avinash is, I don't know if he's on the call, but yeah, he has done some work in potential development for some materials.
Good. We'll pursue this further if it looks like it holds up.
Yeah. That's a great question, great suggestion.
Okay, next question from Pamela Burnley. In some geologic materials, for example, carbonates, twinning is easier than dislocation motion. Are there any metals or intermetallics that show this behavior?
It will depend on what temperature we are. So like here, so this is the general description. And in this case, twinning where you can shift the barriers for some materials that have very low stacking fault energy. I think some of the high entropy alloys are in that category. It's very easy to activate twinning. I think some of those materials will be where you will get deformation twinning, just because the stacking fault energy is so low that you can get twinning in preference to dislocation glide. But it has to do with the relative barrier and the temperature at which you're testing. So clearly that condition, generally what happens in many metallic materials is by the time you are at room temperature, that room temperature will be somewhere here, because FCC metals and other materials, by the time you're at room temperature or slightly above ambient, the dislocation glide stress is very low, unlike in the complex ceramic kind of structures. So for metals, there will be low stacking fault and going to temperatures that are, if not cryogenic, at least below room temperature. I think high entropy alloys have shown some of that. Let's see if Mike has anything to add to that.
No, I think I'm going to break with tradition.
Okay, any other questions?
Okay, we have 3 more questions from Yupeng Zhang. So on pages 24 and 25, there is an initial yield stress. So maybe we'll wait.
So you were talking about this 24. Is this the slide? Or which slide is this? Yeah, go ahead, state the question.
Okay. For viscoplastic deformation, why does there exist an initial yield stress concept from rate-independent plasticity? If it exists, how do you measure it?
So the one that's shown here is, this is a metallic alloy. And it's a metallic alloy. This is the yield stress at which you see onset of plastic deformation. There are different definitions of yield stress, generally by some offset value, about say 0.1 or 0.2% offset plastic strain, which is defined as the onset of plastic deformation. Some of that, I guess, is the definition of what you would call yield strength. This is the stress at which you start to measure a permanent strain in the material.
Right. So, but actually my question is that for rate-dependent material, usually from the constitutive relation, that we have the onset of plastic strain since the beginning of the whole deformation process. So it's not easy to really distinguish the onset of plastic deformations. So for this kind of material, usually that in a constitutive relation, we do not have the concept. We have the concept of reference stress, but we do not, I mean, usually we cannot see the onset of a very noticeable plastic flow for this viscoplastic material. So yeah, that's the question.
But I guess, so you are talking about how to represent it in a constitutive equation. Yeah, I think so. That's a different question than I think what is shown here. This is experimental measure. I think what you are asking is more in the spirit of the constitutive equations and how those are formulated. So I did not cover the constitutive equations, so that would be a different kind of lecture, like Johnson-Cook or the mechanical threshold strength kind of constitutive equation, where I think they will use some kind of a reference in that case. They won't use a yield strength, they'll use. So this is a different thing that is shown here.
Okay, so basically is that even though this is a viscoplastic material, that it indeed has a very distinguishable elastic regime that we can see a very like linear response initially,
yes.
and then there's okay.
Yeah. Oh yes. Yeah, there's a very clear elastic and transition from elastic to plastic.
Okay, thank you.
Okay, we have a few more questions here from Yupeng. The next one I'll just paraphrase. Could you please comment on the common range for strain rate sensitivity exponents M? And the question is motivated by page 28, where M, seems like is very small in the table.
Yep. I mean, generally that is for FCC materials. You could go common range would be maybe up to 0.1. You can see what even 0.1 would be rare. It also depends on the temperature. So if you measure at higher temperature, you might see higher values. I showed earlier that in some materials at elevated temperature, M could be as high as 0.5 or even higher, where you get superplastic deformation. But at room temperature, the values, the typical range will be less than 0.1.
Okay, so for this case, may I say this is almost a race-independent plastic material? It's like
weakly dependent. Certainly for FCC metals, it's a weakly dependent.
Okay.
For BCC metals, it is higher dependent. So in the early slides, I had some flow stress data as a function of strain rate. And you could see, if you go back, you could see that in some materials, depending on where we are in terms of temperature and strain rate range, you might get a stronger dependence versus a weaker dependence. So like here, this is a low carbon steel. So if you measure at low temperature, then you see a stronger dependence than say you would measure at higher temperature. And at higher strain rate, you might see a higher dependence. So it all depends on where we are. And M value is not a constant. I think that's an important thing to understand. For a given material, it's not a constant.
Okay, and the last question here is, when the tangent modulus becomes smaller with increasing strain, should it still be called hardening, or should it be called softening?
I think the nomenclature is that it's still called strain hardening, just with a lower slope. You usually have a strain hardening exponent that has some value n, maybe about 0.3. It might reduce. So I think the nomenclature is to still call it hardening with a lower slope. So I think you are asking about, let me see where it is. In here, right? So you're asking about this. So generally what happens is this is the slope of the stress strain curve. So theta is a slope. If you were to take this and differentiate it, you will get d tau, d gamma. And so that slope is the theta value. So normally the way it is plotted is as a function of decreasing theta value if you go from stage 2 to stage 3. So I have not seen it referred to as softening, it's just a reduced hardening. The strain softening that sometimes is observed is a different phenomena. In some materials, you'll see the strength to start decreasing, and that is called strain softening. And that is due to mechanisms such as formation of a shear band. That's a different phenomenon.
Okay, and then the last question is, where does the power law form, presumably for the strain rate dependence, come from? Why is it a power law form and not some other, like a log law?
Yeah, I think that's empirical. I don't know if there is a good fundamental reason why it is power law. That's where they've seen the data fit. It's more phenomenological. No?
Okay. Any other questions? Okay, well, if there are no more questions, then I wanted to thank everybody for coming, and I wanted to thank Amit for this lecture. We very much enjoyed the humor, especially to help keep us engaged. Once I receive the slides, I will forward them to all of the registrants, and we look forward to seeing all of you on Thursday at 1 p.m. Central for the review session.
Yeah, thank you. Feel free to email questions ahead of time if you have. I'll see you on Thursday.